Right. Hello, everyone. Thank you for coming. I'm just going to jump right in. So this is going to be a little bit different than what you hear usually. I'm going to talk more about black holes and about quantum information. But at the end of the talk, I hope you will see the connection. And that's my goal. And that's why I'm starting with an image of a black hole. If you recognize this, how many of you watched the movie Interstellar? Yes. This is not the movie. So this is Gargantua, the supermassive black hole from the movie Interstellar made by Christopher Nolan. And it's supposed to be it is actually a very scientifically accurate visualization of a black hole. This movie was a brainchild of Kip Thorne, a physicist who works on black holes and wormholes and so on. And his idea was he wanted to have a movie that depicts these objects as scientifically realistically as possible. And so what you're seeing here is a beautiful collaboration between science and art, in the sense that, when you look at Hollywood movies, they have sometimes scientific consultants, but it's never the other way around, right? In this particular case, there has been 2 papers out of this collaboration between science and art. Not only Kip Thorne was a consultant for the movie people consulted Kip Thorne in publishing 2 papers. One of the papers was in Classical Quantum Gravity, the other one in the American Journal of Physics, about this particular visualization. So what they did is they took a black hole solution of Einstein equations, and they looked how null rays propagate when you have an accretion disk around that black hole. So what an accretion disk is, it's just a hot swirling gas and dust, similar to the disk of Saturn. It's on a plane. And then what you see here is the light coming directly from the disk, and also light coming from behind the disk on the top and the bottom of the black hole. So what happens is that the light from behind the disk wants to go away or wants to go up, let's say, and then it's curved by the curvature of space-time through the black hole, and then arrives in your eyes, and that's why you can see behind the black hole. It's as if the black hole wasn't there, but was just the light rays was going around it. So this movie was released in 2014. Back then, we didn't have direct evidence from black holes. It was still, I guess it was accepted that black holes existed. We built a $1 billion detector to detect them, the LIGO. But I remember when I did my master's thesis, I had to collect the evidence, and it was always indirect evidence. And I had to argue that black holes are the most conservative model that explains the observations. Today, we're in a different place, and this is why I start to talk like this. Within less than 10 years, we now have all kinds of evidence about black holes. This is the image that has been taken by the Event Horizon Telescope. You might have seen it in popular media. It's the image of the supermassive black hole at the center of our galaxy. This has been taken by multiple radio telescopes. I think 8 of them has taken images over 5 nights. And the data analysis itself took 2 years. This is called very long baseline interferometry. So what you do is you take the data from all these telescopes, and then you combine them in a way so that these separate telescopes act as if it was a giant dish the size of the Earth. And so you can peek at the center of the galaxy. This particular object is 26,000 light years away, give or take. And it has a mass of 4 million suns. So if you know how big the sun is, you should just, at night think about what a giant object this is. This is as macroscopic as it gets. Why am I mentioning this? We're going to talk about quantum. People think quantum only applies in the microscopic regime. This is not true. We have superfluids, superconductors, Bose-Einstein condensates, neutron stars, white dwarfs, and black holes. These are all microscopic things, and they are quantum mechanical objects. And I will argue that this is the case in the case of black holes. And I hope this is one of the takeaways that you'll take and you'll remember after this talk, months or years from now. If you hadn't known this before, black holes are quantum mechanical objects. And there's a simple line of reasoning that you can see that I hope you will remember. All right, so this is a giant object. More excitingly, we can now measure, we can listen to the universe in this dark spectrum. These are the detectors. I wanted to show these because they don't look like telescopes. These are interferometric observatories. The top ones are the American ones, LIGO. They are the ones who detected the gravitational waves in 2015, which led to the Nobel Prize. That's the one in Italy, in Japan, underground with cryogenic mirrors and so on. This is the one in Germany. So these are the things that listen to mergers of black holes and neutron stars. And what you see here on the y-axis, I'm plotting, I mean, I'm not plotting, this has been made for the LIGO collaboration. This is the solar mass scale. Forget about the x-axis, it's just to make things look beautiful. These little dots are electromagnetic observations. These are neutron stars. And as you can see, there's a mass regime where you can see them. After about, let's say, 2.5 solar masses, you don't see neutron stars anymore, or 3 solar masses. What you then see are black holes. And this is all evidence based on electromagnetic observations. These blue dots are binary black hole mergers. I think this is the one that made it to the Nobel Prize. These are mergers of, let's say, 30, 40, 50 solar mass black holes. And then when they merge, when the two of them merge, they give rise to a larger black hole. And in the case of the first detection, one of the binaries was 29 solar masses, the other one was 30 solar masses. The sum should be 65, but it was 62. So 3 solar masses have been radiated into the universe within seconds. That's a lot of energy in a very short amount of time. So this is one of the most energetic, in fact, I think it is the most energetic event that we know of, a binary black hole merger in the universe. This picture shows the detections from the first 2, what they call observation runs, totaling about a little bit more than a year. And you see, I mean, there's a neutron star merger here, actually, which started, these are neutron stars that give rise to a black hole. That started multi-messenger astronomy. People could see this in the electromagnetic spectrum. Gamma ray bursts, kilonova. So this was a huge development that happened within a few years. And then the third observation run, it's now the chart is full. Currently, we are in the 4th observation run. And you can measure as many as what you saw for the first 2 observation run in about a week or a month. Like almost every day, we get another such merger. Okay, so I'm emphasizing this point because I want you to start with the feeling that this is not just some science fiction topic. It's not just some theoretical idea. These things are out there. And they're out there in the billions, in the trillions. These are black holes. They are huge. They're macroscopic. And they're really there. Like it doesn't, I mean, it's just mind-boggling that we can do this now. So I'm starting with black holes because we're going to make a headway to quantum information. And that's sort of the key for quantum information science in quantum gravity. My goal is just to expose you to these things. So this is going to be on the popular science level. We're not going to find the key to quantum gravity in this talk, I'm sorry. But I hope that you will come out with an understanding of the necessity of it and of its role, of the role that it plays in our fundamental understanding of space and time. And there is some synergy effects between quantum computing, computer science, quantum information, and general relativity. So you will see that some computer scientists like Scott Aronson and so on, they do work on these topics. You will encounter that in your research. So at least maybe you will remember that, okay, this makes sense. So why do people do that? I want to say a few words about that. Because of curiosity. So in the case of quantum mechanics, our hand was forced. Right? If you read the history of quantum mechanics, there were some observations that we couldn't explain. There were some experiments, photoelectric effect, and so on. We arrived at quantum mechanics almost against, I don't want to say against our will, but it's like a crazy theory. You know, if you know, especially the interpretation of probabilities and amplitudes, it just doesn't make any sense. So that was driven by experiments. Quantum computing is today driven by the promise of exciting applications. We may have different views on when these applications may come to fruit, but there is a promise of exciting applications, and that drives a lot of the field. There's nothing like that in quantum gravity. Right? There are no conceivable applications. Maybe if we find this quantum gravity, we will find some, but today nobody can point out any promise of any application. There is no experimental guidance. There is no specific detection or number that you have to explain, and it doesn't match our current existing models. There is nothing like that. So all you have is thought experiments, puzzles. You're guided by your mind. If you're curious, you follow the path. But I think it's important to emphasize that we're not building, I don't know, like a quantum computer by solving the question of space-time. So I want to emphasize a few points as take-home messages, which is I started with this: black holes are macroscopic objects. They're out there. And they have maximum entropy. So this notion that black holes have entropy, and it is a finite entropy, and it's the maximum of any given region, I will explain that with a thought experiment. And that limits the storage capacity of any region of space. In fact, it's also the maximum throughput, like in terms of complexity, for any region of space. Which leads us to a holographic principle, which is then connected to quantum information. So this is kind of the logic. We start with black holes, we find out they have entropy, and then we find out that there's something weird about that entropy in terms of space and time, and that leads us to consider quantum information, and this is where the theoretical research is right now. So if you remember this, my work is done. I will talk a lot more than this, of course, but really this is the part that I want you to remember. Black holes, entropy, information, and then that's where the quantum computing concepts play a role. So I'm going to go back to the black holes again, because we have to understand, not just in pictures and detectors and so on, we have to understand theoretically what they are. And our ideas about what black holes are have shifted over time. There is a concept that is similar to a black hole in Newtonian gravity. And then there is the black hole of classical general relativity. And then there is the black hole of quantum gravity. So this idea changes, and we understand more and more what kind of object that is. So in the Newtonian case, the thing that you learned in undergrad, you have something called an escape velocity. And people in the 18th century thought, Reverend Mitchell and the mathematician Laplace, the Laplace operator, Laplace equations, and so on, they thought, okay, when is this? Maybe the escape velocity will be at some point so large for a large object that you will not be able to see it, because it's going to be the speed of light. So this was the first idea of a dark body. Imagine in the sky there's something so large that you can't see it. And you can calculate that escape velocity very easily by setting the kinetic energy of the object equal to the potential energy in the gravitational field of a large mass m. And you solve it for v. I mean, the little m goes out, and this is sort of the magic about the equality of inertial mass and gravitational mass. So this little m falls out, and then you get this equation for the escape velocity. I think for Earth it's what, 11 kilometers per second. And if you set speed of light here and solve this equation, you get this radius. So if I'm given a mass, I have to squeeze it into such a small radius so that the escape velocity is equal to the speed of light. And this is a small number because g is small, and c squared, that's very large. So that's a very, very small number. For Earth, I think it's the size of a peanut. For the sun is about a kilometer or two. The remarkable thing about this is exactly the Schwarzschild radius of a black hole event horizon. And I think it's related to this equality, the equivalence principle of inertial and gravitational mass. But this is also in some way a coincidence. The dark body of Newtonian physics is nothing like the black hole of classical general relativity. This is an important point. First of all, this thing has a surface. It's like a giant mass in the sky. You can't see it, but you can land on. You will be crushed, but you can land on. Secondly, more importantly, light cannot escape, but you might be able to escape it. There is nothing about acceleration in this calculation. So if you accelerate, you can accelerate away. You don't have to even reach the speed of light. And in Newtonian physics, you can actually pass the speed. There might be things that pass the speed of light and escape it in Newtonian physics. But even if you don't consider that scenario, you can accelerate your way out of this object. So this is different than a black hole, and that difference is important because the way we arrive at this notion of information is when you consider a region of space where nothing escapes from. It's just completely lost. You cannot interact with it. It's gone. And that's, you lose information. So this is the idea where information comes in.
When you say that you can accelerate away from it, do you mean if you're on the surface, any amount of acceleration?
Well, it's not going to be any amount of acceleration, but yes, you will have to put a lot of acceleration on it. And in the special relativistic case, you cannot do that because, speed of light. But in Newtonian physics, if you have arbitrarily enough energy resources, even at a small speed, but with a lot of acceleration, you can escape the dark body.
And that's still in the context of the finite maximum speed. Well,
in the Newtonian case, yes, you can argue it's kind of. So of course, how would you accelerate, right? So you would have to push something that's faster than. I mean, that's a little bit different. If you find a way to accelerate yourself, there is nothing that prohibits this. In this calculation, this assumption is that the speed is constant. So the escape velocity is relevant when you shut off the rocket. You reach that speed, you turn off your rocket. If you are above escape velocity, you will leave the planet. But you can leave the planet without reaching escape velocity. You just have to constantly accelerate. So the acceleration here doesn't go into the consideration of escape velocity, and that's why a Newtonian dark body is not really like a black hole. You can accelerate your way out of it. You can't do that in a black hole. Because, in fact, in a black hole, if you try to accelerate away from it, you fall in faster. Which, you have to do the calculation to convince yourself, but it's a fact. So, real black holes. Einstein published his theory of general relativity, his equations in 1915. And he thought that nobody will be able to solve it. In fact, the math that required him to come up with Einstein equations was so complicated, he didn't know it. He had to consult friends. It's a very complicated math, it's differential geometry. At that time, it wasn't really widely known among physicists. So he didn't think the solution will be easy to find, but within months, to his surprise, Carl Schwarzschild found a solution. And this is like the black hole solution that most people talk about when they talk about black holes. And he found a solution during the First World War. I find this quite remarkable, so I want to read this. This is from a letter that he wrote to Einstein. The war treated me kindly enough, in spite of the heavy gunfire, to allow me to take this walk in the land of your ideas. So if you ever think about working on a project and solving some equations, I don't know if that's the right setting, but he was on the Eastern Front, in the Eastern Russian Front. A few months later, he died from a disease. But he found a solution while he was in the army, calculating trajectories of artillery shells. And so when I say a solution to Einstein equations, what do I mean is a metric. That's the variable in the Einstein equations. So the Einstein's equations are equations for what we call the metric. It's a field in space-time that describes the distances between points in space-time. So in the first image that I showed you, there's a black hole, and now the light curves due to the curvature of the black hole and so on. So the whole process is described by the metric, and it looks somewhat like this. So this is the metric for the Schwarzschild solution. What Schwarzschild did to arrive at the solution was to assume the simplest possible case. So it's a complicated set of equations. You just look for the spherical cow, right? So you assume that the matter distribution is spherical. You assume that there's no dynamical, nothing happening. It's independent of time. And that's what you get. You get an ordinary differential equation, you solve it, and this is the metric. So this describes, so this metric only depends on this little r, which is the distance from the center of that matter configuration. And if this little r is larger than this rs, which is the Schwarzschild radius, then you can see that there is some curvature, there is some dependence of the distances on your dependence of the intervals and the space-time on the distance that you have from the matter configuration, and then you can do some calculations. A lot of the tests of Einstein equations, Einstein's theory was based on these kinds of calculations. But the question then, what happens at this Schwarzschild radius, it wasn't really answered for a very long time, for decades. This was a huge problem in Einstein's theory, and a point of argument, I would say. What happens at the Schwarzschild radius? Because this guy blows up. This is a division, so this vanishes, so 1/0, it blows up, and that's kind of unphysical. Now, I want to say this is nothing unusual where you get an unphysically large singular result in a physical theory, and then you say, this is not physical, I will not consider it. And sometimes people tell this story and say, oh, they should have taken this seriously, and so on. Well, we do that all the time. There's always some unphysical solution and say, this is unphysical, I don't want it. And Einstein himself wrote a paper in 1939 saying that this is like not really realistic, that this will happen because this is such a small radius for a given matter distribution. So there's a story how people arrived at this idea of an event horizon. And I just want to mention it because one, there was a Nobel Prize for it, remarkably, for a math result. And more importantly, because there is an idea of a black hole formation that goes from complex to simple. And this is reflected very nicely in the history of the development of the field. So the idea is the following: a sufficiently large mass in a sufficiently small volume will inevitably collapse to form a black hole. If I can squeeze enough mass into a small volume, I will form a black hole. How did we get there? The first one came from Chandrasekhar. This is another calculation that was done in a weird circumstance. He was actually on a ship in a trip from India to England, and he did a lot of the calculations while on the ship. And his calculation was that, so the idea was the matter will resist collapsing into that small, like I cannot squeeze Earth into the size of a peanut. Matter will resist. Well, how will matter resist? So there was, this is quantum mechanical. Now we go into quantum mechanics. There is this Pauli exclusion principle. Fermions will not want to be in the same quantum state, something called, for electrons, it's electron degeneracy pressure. So there will be some pressure, the matter will resist collapsing. And Chandrasekhar calculated that after a mass of 1.4 solar masses, so if you have enough mass, this is not enough. Like electron degeneracy is not enough, it will collapse. That was the first case where they thought, okay, I mean, we need to find some other way to stop this madness. People then discovered neutrons. Chandrasekhar did this calculation in 1930. Neutrons were discovered, I think, 1932. And then there were physicists, Bade, Zwicky, and so on. They argued that, okay, there's neutron degeneracy, that should be stronger. Maybe that will help. Based on some Russians and other stuff. So Thoma, Oppenheimer, Volkov limit, they wrote a paper, Oppenheimer and Volkov, based on Thoman's results, arguing that there's also a limit in the case of neutrons. They made a mistake, but anyway, so they found a limit that even neutrons will collapse, and they calculated how that collapse will happen. Oppenheimer then later with Snyder calculated the dynamics of that collapse and had this idea of an event horizon, a point of no return, in this 1939 paper. By the way, this was another movie by Christopher Nolan, Oppenheimer, and in the movie they talk about this paper. I don't know how many of you watched that one. Yes, there's a scene where Poland is invaded and they're happy of publishing. So Oppenheimer played a big role in this. And you can see, so this is the point I'm actually making with the slide. Oppenheimer worked on the atomic bomb, right? So this is nuclear physics, this is matter, this is complicated, this is dirty stuff. Then, this is 1939, by the way. Almost 30 years later, 1965, the Penrose-Hawking singularity theorems come. And what Penrose does, this is the drawing by him. He is famous for his beautiful hand drawings. The details don't matter, but the point is, okay, the time goes up. If you have enough mass, you form something. It's a very geometric topological construction. You form something called the trapped null surface. I'm not going to say more about the details, but if you have enough mass, you will collapse no matter what the details are. So nuclear matter, whatever, doesn't matter. Matter doesn't matter. You will follow singularity. Right? And he got the Nobel Prize for this. So now what you form here is a very simple thing. You end up with, I showed you the metric for Schwarzschild black hole. It only has a mass as a parameter. The other ones are constants of nature. 50 years later, there was another solution that was discovered, which is a rotating black hole. It took 50 years to just go from spherical symmetry to axial symmetry, right? This has an additional parameter, angular momentum. And then you can add charge to it, but that's it. So this is a very simple object. After all this, neutrons and electrons and matter and spherical symmetry and so on, all that discussion, what you end up with is something remarkably simple. And that's a beautiful quote by Chandrasekhar. Black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time. So if you remember your statistical physics or thermodynamics, when you have a gas, you describe it with a few functions: pressure, volume, heat, temperature. And there is a lot of stuff that's going on with the gas. A lot of constituent parts, atoms, molecules bumping into each other that you completely ignore. So there is an entropy associated with this, your small description of a large configuration space. And here we have some similar stuff going on. So we only have mass, angular momentum, and charge for a macroscopic objects that can be millions and billions solar masses. Right? Is there something like an entropy? This was a puzzle that John Wheeler, who actually coined the term black hole, posed to his students. And the idea, this is again a thought experiment. The idea is the following: you have a hot cup of tea, or anything that has any entropy. If you want an accretion disk, neutrons, electrons, whatever, and you throw it into a black hole. What happens to the information? What happens to the entropy? Did I, just by throwing this thing out of the universe that I'm accessible, that I have access to, did I just reduce entropy? What happens to the second law of thermodynamics? In a closed system, I'm not supposed to be able to reduce entropy. Now you can say, in fact, Hawking even argued that okay, maybe the entropy goes down. This black hole just is a hole in the fabric of space-time, as they call it, and everything goes out, so I reduce the entropy. But there is a reason to take the second law seriously, and in fact, Bekenstein, one of Wheeler's students, recognized that, and he argued, okay, I want to save the second law of thermodynamics. During that time, when Bekenstein was Wheeler's student, there was another relativist, Christodoulou. He was also Wheeler's student, and Christodoulou and Hawking, they were working on this classical area theorems in classical general relativity. So this is a theorem that describes what happens to the area of a black hole, or of multiple black holes for that matter. And Christodoulou had a concept of irreducible mass, where, so what happens is when you have, let's say, multiple black holes merging, you will never reduce the area, the total area of these black holes. The area will only increase. And the only way where you can have the area not increase is when the process is reversible. This is a little suggestive. There's a reversible process where the area doesn't increase. If it's an irreversible process, the area will increase. And Bekenstein knew about this, and he proposed, okay, maybe the area is proportional to entropy. It sounds like entropy. You know, reversible processes, entropy is constant, irreversible entropy goes up. And so this is the result of the entropy for a black hole, or it's also a coincidence of history. This is Bekenstein-Hawking entropy. And it looks like this. So it's proportional to the area, and there's a proportionality constant that is just purely constructed out of constants of nature. I'm going to name them for this beautiful equation. This is the speed of light from relativity. This is Planck's constant from quantum mechanics. This is the Newtonian constant of gravity from gravity. And here we have statistical physics, Boltzmann constant. So this combines all these separate theories together in one equation. And in particular, this combination, the h bar g and c to the cube, this has actually the units of area, 1 over area. So this is the Planck area, we call it the Planck area. So that square root of this is the Planck length. That's where our description of space-time somewhat breaks down. So summary of this is essentially the entropy of a black hole is given by its area in Planck units divided by 4. That division by 4 came with Hawking's calculation of Hawking radiation. I have another slide on that. But I want to say one more thing about this. So this black hole, this is a huge amount of entropy, right? This is c to the cube. It's a very large number. H bar is a very small number. So this is a huge amount of entropy. And in fact, it has to be, just by thought experiment again, the black hole has to maximize entropy in a given region. So why? You can imagine, okay, we threw a hot teacup into the black hole. You can throw something with high amount of entropy or low amount of entropy. The increase in the area or increase in mass, I mean, it only depends on mass. It doesn't depend really on the entropy of the object that you throw in. So it has to be somehow that while that thing is falling into the black hole, it gets somewhat scrambled and its entropy increases and it gets maximized. Because otherwise there's a contradiction. Right? Then it will be like a cold, something that has lower entropy will not increase the black hole's area as much as something with a high entropy. But what happens is whatever you throw into the black hole, you always get the maximum entropy possible. Which also means that this, in terms of the interpretation of entropy in terms of information, so this is the maximum amount of information that you can store in any given region of space time. In that sense, it's a computer science theoretical object. The maximum amount of entropy that you can, the maximum storage capacity of a region of space. So if you manage to build a quantum computer that has the maximum amount of capacity, you're going to build a black hole. So this is the moment when the classical becomes quantum, right? So you have a classical black hole, which some people say it has no entropy. It's actually not true. Classical black hole actually has infinite entropy. This is a bit technical, so I'm not going to go in there. But in the classical case, you don't really normally talk about entropy of a black hole. But you realize this is a region of no interaction. The information gets lost. So if you have such a region, without knowing any equations, you can remember that you can throw a hot teacup in it. It has to have some entropy. You don't want to reduce entropy of the universe. So you have to have some sort of limit, some sort of finite expression for the entropy of the black hole. It has to be proportional to its surface area, because that's more, of course, technical. But the idea is that the black hole only has a surface and you don't know what the volume of it is. But this poses a challenge. Look, this is another puzzle now that comes up with this formula. Why is the entropy proportional to the area? Normally in statistical physics, when you calculate entropy, it's the size of the space of configurations. And that's proportional to the volume, obviously. If you have a lattice, a cube, and so on, it's proportional to the volume. In this case, it's proportional to the area. That will lead us to holography. But before I go to holography, I want to say one more thing about the Hawking radiation, because this is another area where quantum information plays a relevant role. After Bekenstein's paper, Hawking was skeptical. They published another paper showing that there is some analogy between black hole thermodynamics between black hole physics and thermodynamics. But they thought black holes don't radiate, so this just is a formal analogy. It cannot be the case that actually the black hole cannot actually have entropy, Hawking thought. But then talking with Zeldovich and so on, he realized maybe if you combine a little bit of quantum mechanics, you will get a radiation. And in fact, you do. So you get this Hawking radiation. This is, I think, engraved in his grave. The Hawking radiation is inversely proportional to the mass of the black hole. And again, you have the constants of nature here. And if you know the Hawking radiation, you can go to the entropy and vice versa. This is just basic algebra, really. These things are connected with each other. So what does Hawking radiation mean? the black hole is actually not black in the sense that nothing comes out, but it's black in the sense that it radiates a black body in the black body spectrum. So this title, black holes are black. This black refers to the darkness of the black hole. This black refers to its radiation. It radiates, and it radiates at a temperature that Hawking calculated in 1974. This is actually what I think in the scientific circles, Hawking is most famous for this realization that black holes do radiate. That gives you another puzzle. So now you have a black hole. You form, let's say, quantum mechanically, and I assume you all know about unitary evolution and quantum mechanics and information preservation. You can form a black hole from pure states. Let's say I prepare some pure states, I throw them in, forms a black hole. And then this black hole will radiate at the Hawking temperature for a very, very, very long amount of time, but eventually it will evaporate. After it evaporates, nothing is left of the black hole. But what you all are left with is thermal radiation in black body spectrum, which is a mixed state quantum mechanically, right? It's a probability distribution. So this is, you cannot have evolution from a pure state to a mixed state, which is unitary. And that breaks a fundamental principle of quantum mechanics. You have to have unitary evolution. By the way, anybody has any questions, anything is not clear, please just shout into the room. I'm assuming that you all know about unitary evolution and unitariness, and what that means in terms of preservation of amplitudes and so on. So if you throw unitary evolution out, you get all kinds of crazy stuff, right? So there's this, actually I recently learned about it, I should have known this, but there's a theorem, Riesz-Leiter theorem, which I think everybody should know. It says that in any, maybe I shouldn't tangent, but in any given region of space, you can put a local operator that does an arbitrary thing somewhere entirely different. Like I can apply a local operator to a region of space in vacuum, and then I can construct Jupiter miles or thousands of miles away. The thing is, it's a very crazy theorem. It has been proven in the 1960s. The only thing is that that operator is not unitary. So you cannot physically do this, but this points into this huge entanglement in the vacuum state in quantum field theory. Anyway, the point is unitary evolution is important. And so we want to maintain that. And this goes, there is another tangent to it that goes into quantum money, like can you decode, if you assume that the Hawking radiation is really entangled with the black hole, how can you decode that information and so on? So that you will encounter that. That's why I wanted to mention it. All right. Back to the timeline. This is the paper by Bekenstein from 1972, where he says that the black hole entropy as the measure of information about a black hole interior, which is inaccessible to an exterior observer. So this is the thing where, again, I want you to remember the information is inaccessible to an external observer, so you want to have some notion of entropy coming into the classical picture of the black hole. And that entropy is equal to the ratio of the black hole area to the square of the Planck length times the dimensionless constant. So it's the area in Planck units, right? So why the area? And that brings up the holographic principle. It's a bit weird that the maximum amount of information that you can contain in a region of space is proportional to its surface area. This, by the way, is independent of black holes. We came to this conclusion by considering black holes, but it's independent of them because it applies to any region of space. Once you put sufficient information, it will have to collapse into a black hole, and that will then maximize the entropy that you put in there. So any given space, any given region of space is somewhat pixelated on its boundary surface, and each pixel corresponds to a Planck area, and that's the maximum amount of information that you can put in. So the three-dimensional world of ordinary experience is a hologram. A hologram is, a two-dimensional thing that encodes a three-dimensional picture. An image of reality encoded on a two-dimensional surface. It's just weird. This was argued by Tuft and Susskind in the early 90s, and there's a realization of this idea by Juan Maldacena in 1997, which happened in string theory. So what Maldacena discovered is that there is a duality, there's a correspondence between a kind of space that has gravity and a kind of quantum mechanical field theory that has no gravity. So this is a duality between two things, one with gravity, one without gravity, one in a higher dimension, the other in a lower dimension. And it's an idea that space-time emerges from something that's lower dimension, like this emergent space-time that you might hear once you do your research in quantum computing and people talk about decoding of entangled states and so on, that space-time emerges from quantum entanglement. Yes?
There are simpler examples of photography that go back earlier. You can think topologically.
Topologically, like
Topological theories instead. And those go back to mid-80s.
you mean before the context of string theory?
Yes.
Okay, yes.
Yes.
But I think the holographic principle as such has only been formulated in the 90s based on the black hole.
There's a general sense of holography and then like holography only in the context of gravity. That's nice. But it's just general holography. You go back earlier.
Nice. Okay, I don't know. Maybe I can ask you. But so when you say general holography, what do you mean? If not in the context of gravity?
I mean, insurance rights.
Oh, Chern-Simons. Yes, that's true. Okay, got it. Yes, this is like space-time entanglement arising out of entanglement. So this is a duality between two disparate physics, gravity and an antide Sitter. So antide Sitter space is a kind of space that is a solution of cosmological solution of Einstein equations. It has a negative cosmological constant, and it kind of looks like this. So what I pictured here is I wanted to show you this picture because I'm going to connect this to our program, quantum math. So this is kind of time goes up, and the three-dimensional world that we consider is a negatively curved space. Does anybody wonder what I mean when I say negative curved space? Good. So this is a negatively curved space, hyperbolic geometry. This is the famous Escher drawing. And so the time slices are negatively curved spaces. And that's important because we have people working on these things. In fact, so Alicia Kohler, who was part of the MathQuantum effort, they create, using hyperbolic geometry, they create hyperbolic lattices in the lab. And with such hyperbolic lattices, you can actually make kind of lab experiments that test certain predictions of this antide Sitter conformal field theory correspondence. So some of the motivations of doing these things come from that. And this has applications. I think I will mention the applications. And tomorrow there's going to be a talk about this if you're interested. I will definitely be there. This is about hyperbolic quantum error correcting codes. So the hyperbolic geometry plays a fundamental role in understanding the holographic principle. And we have people working on it, and if you're interested, you should contact them. There are other applications that are, this describes strongly correlated electron systems, quantum phase transitions, quantum gluon plasma. As I mentioned, holographic quantum error correction. I'm going to just talk about entanglement and complexity in the next few minutes. And I'm really just going to scrape the surface. I'm going to go through it really fast because to go into any depth, even just if you want to talk the entanglement part or complexity part, you can talk about it for a semester. But the point again is that you appreciate this idea that black holes as a region of space of no return necessarily come with a notion of entropy, which implies maximum storage for this region of space, which implies something like holography, the surface, as opposed to the volume. And then it goes much deeper than that. So this is an example of holographic application where people talk about quantum entanglement. This is if you want to calculate quantum entanglement entropy for a field theory. So it's okay to do it in finite dimensional Hilbert spaces, but if you have quantum field theory and you want to calculate entanglement entropy, For a conformal field theory, it's very difficult. But Ryu and Takayanagi in 2006, based on this ADS-CFT idea, proposed a duality between entanglement entropy and geometry of the bulk, like the geometry. So this is again ADS as a universe in a bottle. And there's a theory on the boundary, just on the boundary. And then there's a region A and a region B that are separated from each other. And then you want to calculate the entanglement entropy between these two regions. And what they showed is that this entanglement entropy is equivalent to in this case, the length of the geodesic that connects these 2 points. So in general, for a high dimensional case, it's the area of the minimal surface that connects the boundary points in the bulk. Why am I mentioning this? Because it's a duality, and MathQuantum is all about synergies between different areas. And in this case, this is a duality between geometry, like really a pure mathematical differential geometric notion. You can calculate the area of minimal surfaces very easily. It's an extremization problem. You can do it in 2 lines. Whereas the calculation of the quantum entanglement for a conformal field theory takes, it's very difficult and takes pages and pages, and it's not clear usually how you do that. So such dualities can be really powerful, and this is an example of something like that. So sometimes problems, when you think about them from a different perspective, you can solve them much easier using math. Homologous, yes. Yes. There are many details. So this is the simplest case, time symmetric. This surface has to be homologous to the boundary in higher dimensional that matter. But I don't want to get to, this has been generalized to the dynamic case. This is only for the static case. Well, all of these are conjectures, but there's sufficient evidence. Yes, so I would say there's sufficient evidence that will satisfy almost all physicists and even some mathematicians, but not. But this is disputed. So
the formula gives reasonable answers.
The formula gives the same answer. So what happens here, for example, in this particular example, you can actually calculate in this case. So this is ADS3 CFT2. So 2-dimensional conformal field theory on the boundary and 3-dimensional anti-de Sitter space. You can calculate explicitly the entanglement entropy. And then when you calculate the length of the geodesic, you see that it's the same. And how is it? There is something called a central charge. You have to know a little bit more about the asymptotic symmetry group of ADS. But given that background, they are the same. And there are many examples where you calculate one thing in one side, it's the same. If you can calculate the other side, it's the same. And if you can't calculate the other side, you argue that it's a reasonable answer. In that sense, it's a conjecture. But for like all general cases, there's no proof. There's actually somewhat like something like a proof by Maldacena about this particular conjecture, but I don't know if that will satisfy a hardcore mathematician. But you can do these things with actual hyperbolic lattices. Like you can really calculate, you can really write, you can build. So this is what did they do? So this is a 6-qubit system. So 6-qubit nuclear magnetic resonance quantum simulator. So you can build these things and you can test these conjectured dualities in the lab. And Alicia Kohler is doing part of that. And here you see, this is kind of a representation of hyperbolic space with qubits, a 6-qubit resonator. And then you can say, okay, here I can calculate the entanglement entropy, and I can calculate the length of the minimal curve in this case. And then are they equal? And they find, I think, in their paper about 85% equality, and they explain that difference based on decoherence and noise and so on, and they can improve their results. So there is really something that you can do in the lab with these things. There is something that you can do on paper with these things. But this is an area where mathematics, just like differential geometry in this case, plays a role in understanding quantum computing and quantum systems. And there is something similar with complexity. I think I will not go much into this. Complexity is a measure of how many operations you need to prepare a given quantum state. And the space of quantum states is exponentially large. And that gives you exponential time to explore the space of states. There's a conjecture, again, motivated by the holographic principle, which argues that the volume inside the black hole is a measure of the complexity of the quantum system that is on the boundary. And this conjecture is really weird because the observation is that complexity grows linearly in time, and you can then calculate a certain definition of volume. So this is a little bit technical, but the volume in the case of relativity depends on the observer. There is no invariant notion of volume inside the black hole. But if you say, okay, I'm just interested in the maximal volume inside the interior that connects the wormholes together and so on, it should grow linearly in time. And so I now conjecture volume is complex. This is a wild conjecture, but there's now a lot of evidence. I mean, this is due to Susskind, who's famous for his conjectures. You know, you find something that grows linear, something else that grows linear, and you say that's it. Well, it turns out to be almost true, more or less true. And again, like there's Nicole Younger-Halpern, who is also involved in our effort in MathQuantum. They published this paper where they show that the linear growth of quantum circuit complexity is actually true. They have a proof that the complexity grows linearly, and then there's a threshold which exponentially grows with the number of qubits. So there is research about these things within the MathQuantum effort. Okay, that's it. I'm going to repeat what I told you, at least what I want you to remember. Black holes are macroscopic objects. They're really out there, trillions of them. And then just by this idea that a black hole is a region of space that you cannot interact with, they must have entropy. And that entropy is a quantum mechanical concept in this case. It gives you the maximum storage capacity for that region of space. And because it's the region of space that is bounded by the surface, that you can only have access, you can only kind of see the surface of it, that implies the holographic principle, which is deeply connected with quantum information. All right, I'm going to leave some time for questions, and if you have some feedback, here's the link. Thank you.